Hello and welcome to the section on simplifying radicals. We first look at things that come out nice. We did an entire exponent monster where we had something like 32 to the 3/5 power. And we did the fifth root of 32. We looked right down here, 32. Fifth root is 2 to the third power is 8. Remember how we defined rational exponents and how they need to be defined is that this is 32 and this is the fifth root of 32 and cubed. So this is how you transfer between exponential notation with fractions and radical notation. So a radical has that little doohickey right there. And it's just a different way of writing it. And sometimes it's nicer this way because you have all the power of fractions. And sometimes it's very handy to write it this way. So we look at that and the fifth root of 32 came out very nice. Now, nice actually has an official word for it, and it is rational. This is when we had the whole breakdown of the whole number system. Anything that comes out nice with square roots turns out to be rational and is in Q. Now, when we get the not completely nice, there are some of those as well, but let's look at some of the nice ones first. So any of these guys will come out nice. If we have like the square root of 4, it's going to come out nice. The square root of 9 is going to come out nice as 3. Square root of 36, etc. All the way up square root of 256. They all come out nice. Cubes. So if you ever see the cube root of 8, it comes out nice. The cube root of 27 comes out to be a 3. The cube root of 125 comes out to be 5. So any of these guys come out perfectly in the cube root world. In the fourth root world right here, any of these guys, they come out exactly right on in the fifth root. So if you had the fifth root, just like we did up there, the fifth root of 32 comes out nice. The fifth root of 243 is 3. And then sixth root, perfect, seventh root, perfect, eighth root. Now what's interesting is when you look at this in prime factorization mode, this is exactly why it comes out. When you do the prime factorization of 243, you will get 3 times 3 times 3 times 3 times 3. It's like a 5 of a kind going on, and that is what undoes the fifth root and makes it come out nice. Other things that come out nice. The square root of x squared. That comes out nice. All positive numbers turn out to be an x. With negative numbers, it turns out there's an absolute value thing. We're kind of going to stick with positive numbers for a while. But yeah, square root and x squared go away. In the cubes, it's the cube root of x cubed that works. But also know what other powers come out nice. You can take the square root of x to the fourth and the square root of x to the sixth. That's going to be x cubed. And it's nice to think about this as, remember, this is a 1/2 power. So any power that is even will be able to take a perfect square root of. Any power that is a multiple of 3, so x to the, say, 12th, if we take the cube root of that, that's going to be x to the 4th, because 12, 1/3 of 12 is 4. So in here, we've got to have a perfect x to the 4th or a y to the 16th before we can fourth root it perfectly. Anything that doesn't turn out to fit this pattern is not completely nice. So on this same board while we're writing it, we're going to write some not nice ones. If you have something like the square root of 7, this is what we would call irrational, which means this number, the simplest it can go is to look just like that. It's a decimal that never stops and never ends. This is an irrational number. We can't write it as just a fraction of two integers, a ratio of two integers. So the square root of 7 kind of stays right there. Our job is to simplify everything nice that we possibly can. Let's look at some other things like cube root. If cube root of any number that isn't in this list or in this pattern of cubes doesn't work. So if you have the cube root of, say, 4, that does not come out nice. Remember, 4 breaks down to 2 times 2, but we need a 3 of a kind in order to undo a cube root. So we would have to have the cube root of 8 to make it work. If you have like the fourth root of, I don't know, 27, that doesn't come out. 27 is in the cubes list, but it's not in the fourth. So these are all irrational numbers. However, there are some irrational numbers that turn out to, well, let's look at this, square root of 12. That is definitely an irrational number. It's not nice. 12 is not one of these numbers. However, you do need to recognize that, wait a second, 12, if you break it down into prime factorization, you get 2 times 2 times 3. Notice that part of the number, this 4 right here, I'm going to rewrite it as square root of 4 times 3. The square root of 4 does simplify, and we get 2 square roots of 3. We have to see this in a calculator. This is actually pretty cool stuff. If you punch in the square root of 12 up there, you get this, the beginning of that number in decimal notation is right here. Now watch what happens if I punch in 2 times the square root of 3. This is, we get the exact same number. These are the same thing, but yet the 4 that was part of the 12, the square root of 4, can be simplified, and so we do it indeed. So we're going to work on simplifying these radicals that, even though they don't go completely nice, they do go pretty far. And what it means is that if we're dealing with squares, we have to take out any time that number is there. Let's try one more right up here. If we had something like the square root of 50, that is not a nice number. But is there a nice one in there? Well, yeah, this is 25 times 2. What's the square root of 25? Well, that's a 5. But the 2 has to remain in that irrational, not nice world. And 5 square roots of 2 is the exact same thing as square root of 50. Let's do one with a cube root. Again, let's write it not nice. If we have, say, the cube root of 54, let's say x to the 7th. Ooh, let's clear up some room down here. That's better. Do we see any perfect cube that goes into 54? We got to be in the cube, so 27. You see that's 27 times 2? Now, if you can't identify that, you might have to do prime factorization. Break it down, and you get 3 times 3 times 3 times 2. When you see 3 numbers together, you know that you have a perfect cube. So that's going to be 27, and cube root will be a 3. Now, so this guy, I'm going to do it in really slow motion here. We break it up into 27, which is a perfect cube, times 2. So that guy is going to escape this irrational world. Now, x to the 7th, is that a perfect cube? It isn't. But we do know that in order to take a perfect cube of a variable, we need a perfect multiple of 3. So x to the 6th is going to, yeah, you can cube root that and you get x squared coming out there. So you have an x left over. So this guy right here gets to come out, and this guy right here gets to come out. So we get 3 cube root of x to the 6th is x squared. So cube root of 27 is 3, and we see that right here. Cube root of x to the 6th, in slow motion, cube root of x to the 6th, that would be x to the 6th thirds power, which is x squared. Comes out exactly nice. And then these guys are stuck in there, 2 and the x. So that the 2 has to stay in and the x has to stay in. This right here is as simplified as it can be. It doesn't look simplified, but the reason it is we have taken, and everything that can be made into a nice number has stayed there, and those that remain in radical notation have to remain there. And this is all just multiplied together, sitting next to each other. That's kind of cool. That's how you simplify these irrational numbers to be as rational, or as close to rational, or have as many rational components as humanly possible. What's amazing about these numbers, these irrational numbers, is that sometimes they get multiplied, and if you're multiplying by the right thing, they come out of the irrational world. I'll show you what I mean. When we take something like the square root of 2 times the square root of 7, it becomes the square root of 14. That kind of makes sense, right? They're both square roots. And really what's going on, you have 2 to the 1/2 power times 7 to the 1/2 power, and that it will be the same thing as 2 times 7, all to the 1/2 power. If they're the same power, then they could be lumped together like this, all to that power. So yeah, square roots can times, or cube roots can times together, and that's great. This is as simple as it goes. However, if I do something like square root of 2, cannot be simplified, and I times it by the square root of, say, 10. Square root of 2 times square root of 10, that ends up being the square root of 20. Now, the square root of 20, does does that have any of those perfect squares in it? Yeah, it does. Well, we don't want to write it as 2 times 10, that won't help, but 4 times 5 now. What's the square root of 4? 2, and the 5 is still there. So this thing, when we times it, the square root of 2 was able to find another partner in here, another 2, that made a 4, that came out of the irrational world. The most common example of this is when you have something like the square root of 7 times the square root of 7. Well, square root of 7 times square root of 7 is square root of 49, and that equals 7. Whoa! Let's pull out the calculator. We need to look at why square root of 7 times square root of 7 equaled 7. All right, pull that guy out. Now, when we put this guy on and we say, what is the square root of 7? Notice this number right here, 2.6457513111 dot 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 dot. When he multiplies himself, this is what square root means. When this number times himself, we get the number 7. And notice how that works over here with the numbers. When this times itself, we better get 7, because that's how the square root of 7 came to be, is that the square root of 7 times the square root of 7, square root of 7 times itself would equal 7. So yes, it comes out just right. But notice that they have these partners that will help get them out of the irrational world. Sometimes it does it, sometimes it doesn't. So for example, if we had square root of 24, let's take times the square root of 30. Now you could multiply these two together first and get some crazy big square root of 720 or something like that. Or you can simplify them first. So let's try this one. Square root of 24. Is there a perfect square in there? Such as, well, I always try 4 and 9 and 25 and 16. And yeah, 4 is in there. This is 4 times 6. And so this square root of 4 is 2. So this is 2 square root of 6 times 30. Is there anything in there? This is 5 times 6. No perfect square goes in there. No 4, no 9, no 16. So we're stuck right there, square root of 30. So when we multiply these two, we get 2 square roots of 180. Oh boy, does 180 have a perfect square in it? I actually not really sure. So I'm going to do a prime factorization on that. 2 and 90, 9 and 10, 3 and 3. Oh, there's going to be one square, and a 2 and a 5. So if I were to write out the prime factorization of this, I get a 2 and a 2, and so that makes a 4, and this is a 9, and that's a 5. So this is, oh yeah, that's 9 times 20, which is times 4 times 5. Okay, so yes, we have perfect squares here. What's the square root of 9? 3. So we get 2 times 3 times the square root of 4. And then the 5 has to stay there. So we get 6. The answer is 12 square roots of 5. Fascinating. Look at that. We times it up there. And even though we could only pull out a 2 to begin with, this guy was a 6 times a 5. And so when we multiplied him, these 6's now became a 36. And square root of 36 was this new 6 that popped out of the irrational world. Square root of 6 times square root of 6 was 6. And wow, that's kind of nice. Sometimes they simplify down like this, and sometimes they come all the way out into the nice world, the rational world. Let's look at something like square root of 18 times square root of 98. Oh, looks like an ugly problem to begin with, but again, we're in the square roots, so let's find perfect squares. So what can go in here? This is 9 times 2. Good, square root of 9 times 2, square root of 9 is 3 square roots of 2, that's that one. And we're going to times that by, 98. What is 98? 2 goes into that. 49 times, oh yeah, look there, we've got a perfect square, 49. So this is 49 times 2. Square root of 49 is 7 square roots of 2. We're timesing these two together and we get 21. Square root of 2 times square root of 2 is square root of 4, which is 2. Oh my word. Let's pull out the calculator and see if that actually is true. Does it really happen if we were to take the square root of 18 times by, oops, get that parentheses on the end of there, times by the square root of, there we go, 98, will it really turn out to be the number 42? And you're like, math is true. Look at that. When you simplify, all you're doing is taking the square roots of any numbers that actually take the square root. And when you multiply, sometimes they will meet up with their partner to get them out of the irrational world, and you need to simplify those as far as you possibly can. Excellent. You know, way back in the good old days, as we start talking about how to add and subtract these things, we had stuff like 2 sheep plus 3 sheep, and what does that equal? Well, that equals 5 sheep. And we had 2 sheep plus 3 penguins, and what does that equal? Well, it doesn't. You can't add those things together until they are like terms. In fractions, we required common denominators or labels in order to add them. Same thing happened when we got to variables. We had 2s plus 3s, and look at that, we got 5s. When we had 2s plus 3p, it didn't happen. Well, the same thing is going to happen here. If we have something like the square root of 8 plus, I don't know, something like the square root of 50, we try to add these two together, they are not the same thing. Square root of 8s and square root of 50s are different items. They're in completely different worlds. But if we look at this and we say, okay, can this simplify down? Well, yeah, that's 4 times 2. That's nice. We get 2 square roots of 2 right there. Square root of 50, does that simplify down? Yeah, that's 25 times 2. So we get 5 square roots of 2. And now you look at this, 2 square roots of 2 and 5 square roots of 2. Doesn't it just have a ring to it? Yeah, you have 2 of those thingies and 5 of those thingies, which are the same thingies, and they end up being 7 of those thingies. And that is how we add and subtract irrational numbers, especially when they're in like a binomial like this. If there's anything that is alike, it can add together just as though these are like variables, because they are things, they're labels, they're denominators, if you will. So if we have something like 2 plus, let's write that a little bit better, 2 plus 3 square roots of 7, and we minus the irrational number 5 plus 8 square roots of 7, all we're going to be doing is combining like terms just like we did in polynomials. The negative will come in here, and we have 2 plus 3 square roots of 7 minus 5 minus 8 square roots of 7. And so the 2 and the 5 become a negative 3, and 3 minus 8, that's minus 5 square roots of 7. And that's exactly what we have right there. However, this actually brings us to a point where we're going to go back and see some multiplication. It's kind of fun. So let's, instead of adding these two, what if we times 2 plus 3 square roots of 7, and we times 5 plus 8 square roots of 7? Now we're adding and multiplying at the same time. In this case, they are like binomials. So we are going to distribute. 2 times 5 is 10. 2 times 8 square roots of 7, that's 16 square roots of 7. Good. Times these guys, and now we have 15 square roots of 7. And 3 square roots of 7 times 8 square roots of 7 is 24 square roots of 49. Again, look at how genius that is. When we took a square root of 7 times the square root of 7, it popped right out of the irrational world. Square root of 7 times square root of 7 is indeed 7. Fascinating. It works exactly like when we had x's here, except sometimes it moves from not completely nice, bam, and we pop out in the rational nice world. So let's simplify what we have here. Collect these like terms, and we have plus 31 square roots of 7. And then we have 10 plus, 7 times 24. That is 168. So 10 and 168 is 178. Now, commonly it will be written with the rational, nice piece first, and then anything with a radical on it will be written second. That's a normal way to write it, but if you were to write it the other way around, 31 square roots of 7 plus 178, it wouldn't be a miss at all. Let's try one more of those and see how it looks. How about 7 minus 2 square roots of 6 times by 3 plus, should we keep it in the family and make it a square root of 6 or make it a little bit different? 5. Let's do it with a square root of 6. And let's see what happens there. All right, so when we multiply them, we get 21. And plus 35 square root of 6. And then minus 6 square roots of 6. And then minus 10 times square root of 6 times square root of 6, 6. It popped right out of there. That's pretty fascinating. So collect these like terms. We have 35 minus 6 is 29 square roots of 6. And that's how it's said is, well, we have 29 of those square roots of 6. And we have 21 minus 60 is what that is. 10 times 6 is 60. So 21 minus 60 would be negative 39 plus 29 square roots of 6. Excellent. That's how multiplication and addition and subtraction kind of work together. You'll treat them just like variables until they multiply together with the correct partner to get out of the rational world. Otherwise, they'll stay in there like a variable. And like square root of 7, square root of 6, different things. Right here, these could not combine until you get them exactly alike. Excellent. Let's move on to the last part, division. Division actually takes two different faces. Division of radicals, sometimes we're not punching them into to get decimals. I mean, we could do that, but if we leave them simplified and exact, now that's what's interesting. If you turn them into decimals, you actually didn't write out all the decimals that are there. So leaving it in exact form is a little bit tough. So division actually means we are going to take the convention that we are going to rationalize the denominator. That's a big phrase, and so we better see what it means. If you have something like 5 divided by the square root of 2, these actually don't combine and simplify, but we're going to accept the convention that we need the denominator, the bottom number, to be rational. We need it to be nice. So we're going to go back up here into our multiplication genius that we found and say, wait a second. In division, we actually are going to be rationalizing the denominator, so we need to times top and bottom by something that will allow this to leave the irrational world. Well, if we times it by that, what happens? We get 5 square roots of 2 on the top. He's ugly, irrational completely. But what is the denominator? The denominator is square root of 2 times square root of 2 is 2. This is how division of radicals happens. This is considered a simplified form of that, is that you times by something that will allow it to leave. All right, let's try another one. 5 over the square root of 7. And what are we going to times top and bottom by? You're like, oh, I know that one. Times it by the square root of 7, times it by the square root of 7, and you end up with 5 square roots of 7 over 7. You're like, well, that doesn't even look any nicer. You're right, but the denominator has been rationalized. So there is your answer right there. Now, sometimes it turns out to simplify once you get to the end. Something like 6 over the square root of 12. Now, let's be careful here. The square root of 12 can simplify. So this is actually 6 over, let me see, square root of 12, is there a perfect square in there? Yep, 4 times 3. So this is actually 6 over 2 square roots of 3. Well, 6 over 2 is 3. So this is 3 over the square root of 3. All right, let's complete it. We've got to rationalize that denominator. So go back into the multiplication world. Times by square root of 3 times by square root of 3. And we get 3 square roots of 3 over 3. Oh boy. Those 3's divide out to 1. They cancel. No. 6 divided by the square root of 12 simplifies to the square root of 3. Yeah, rationalizing the denominator puts as much as possible into the rational world to see if anything's going to simplify. I got to check that out. Let's see if that's really true. The square root, no, 6 divided by the square root of 12, right? 6 divided by the square root of 12, that is that number, 1.732050808. And if we did this correctly, the square root of 3 is the exact same thing. Holy smokes. Math is genius. Love it. All right, so let's go and see what happens when we don't have perfect squares going on there. Let's try something a little bit tougher. If we have 7 over, let's say, the fifth root of x squared. Now, you might be tempted at the onset to say, oh yeah, we know how to do this. We've been doing this forever. Let's times this by the fifth root of x squared. And the fifth root of x squared, you just times by what's there. Well, did that actually work? Well, we got 7 times the fifth root of x squared. That looks incredibly inappropriate right up there. That's terrible. It's ugly. However, what did it do to the bottom? We now have the fifth root of x squared times x squared is x to the fourth. We failed. Oh, epic fail. The whole goal in multiplying was by multiplying by something that would allow it to leave the world. When you're a square root, you're multiplying by something so you have a square. But if you're in a fifth root, what power do you need here in order to get out of the fifth root world? You need a fifth power. So it's not that we want to multiply by the exact same thing. No, 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 no. We need to multiply by something that will make it so when we times these two together, x squared times x cubed, we get an x to the fifth. Okay, so I just covered those up. X cubed, so we've got to multiply by its partner, not just by itself. Now, but square roots, they are their own partner because you square them and they get out of the world. But when you're not dealing with square roots, you actually have to multiply by its partner. Good, so this 7 fifth root of x cubed all over, now this becomes x. See how we rationalized and took that radical notation off by multiplying by the partner. Let's try another one like that. That was kind of crazy. 3 over the seventh root of y. Now let's think for a minute. What is that partner? What power do we need here to get out of the seventh root world? We need a y to the seventh. So we've got to times by the seventh root of y to the sixth. Y to the sixth? Why y to the sixth? Because it is y to the sixth times y, when we multiply those, become a perfect seventh power. So we will end up with 3 seventh root y to the sixth on the top, and on the bottom we get left with the seventh root of y to the seventh. Let's write that out in slow motion, which, whoosh, whoosh. Yeah, this is 3 times the seventh root of y to the sixth all over y, rationalizing the denominator. One last thing on division before we let you work on some for yourself. You may have a binomial in the bottom, something like 2 over 3 plus the square root of 7. When you have something like this, 2 over 3 plus the square root of 7, and you're like, okay, we're going to rationalize the denominator. Your initial reaction would be like what happened before. You're like, oh, we could do this. Let's times by 3 plus the square root of 7. 3 plus the square root of 7. Now, we're going to do this in slow motion and let this failure happen. We have to watch it. Even if you think you know why it's going to fail, you need to watch it anyway. On the bottom, let's multiply 3 plus the square root of 7 times 3 plus the square root of 7. We will, 3 times 3 is 9. 3 times square root of 7 is plus 3 square roots of 7. 7 times 3, square root of 7 times 3 is 3 square roots of 7. And square root of 7 times square root of 7 is square root of 49, 7. Can you see that we will be left with radicals on the bottom? All right, bad news. That's not good. That's not going to work, so we can't do that. Others will look at that and say, oh, I know what to do. We can times by the square root of 7 on the top and the bottom, kind of like what we did last time. On the top, we get 2 square roots of 7, but what happens on the bottom? Because of this plus sign, we're going to have 3 square roots of 7 plus, hey, square root of 7 times 7. It fixed it there, but it put a square root of 7 on there. We're like, what could we do? Let's go back, way, way back, and remember something that happened long ago in our math history. We had a special pattern where when we took x plus 3 times x minus 3, do you remember the magic that happened there? We got x squared minus 3x plus 3x minus 9. These middle terms canceled and we were left with x squared minus 9. We got a difference of squares, a perfect square there and a perfect square there. And these guys weren't called opposites of each other, they were called conjugates. So they were partners in crime to allow this magic to happen. We're going to do the same thing here. If we times by not the exact number, not just the square root of 7, but by its conjugate, 3 minus the square root of 7, 3 minus the square root of 7, notice what happens. You're like, hey, can you do that? I'm timesing top and bottom of a fraction by something. I can multiply by anything I want because I haven't changed the fraction at all. This is just a special fancy 1. All right, let's see what happens when we times it. 3 times 3, so let's put these parentheses on here. So they're binomials. So 3 times 3 is 9, minus 3 square roots of 7, plus 3 square roots of 7. And notice what just happened. The things that are going to be left with square roots cancel, just like that magic way long ago. And then square root of 7 times square root of 7 is, so minus square root of 7 times square root of 7 is a 7. Yeah, that's pretty slick. Those guys now go away. And on the top, we have 2 times 3 minus the square root of 7. And sometimes what you're left with, now, first of all, you should note that the bottom is now a rational number. That is rationalizing the denominator. And sometimes it will simplify with what was up on top. And in this case, it happens to do it. This number right here in that blue color is the same as 3 minus the square root of 7. That's amazing. Look at how that simplified down. Let's do one more of those and then let you on your own. 5 over 2 plus 3 square roots of 6. Ooh, let's try something like that. So we are going to multiply by something that will allow this entire binomial to get out of the irrational world. And in this case, we're going to have to make sure that it squares both pieces, which is by the conjugate. So we're going to times by 2 minus 3 square roots of 6, 2 minus 3 square roots of 6, and when we multiply that out, on the top we get 5 times 2 minus 3 square roots of 6 over, let me see, 2 times 2 is 4, 2 times that, that's minus 6 square roots of 6, that times that is positive 6 square roots of 6. The magic of the conjugates just happened, and at the end we get minus 9 square root of 6 times square root of 6 is 6. So 5 times 2 minus 3 square roots of 6 over 4 minus 54. That's a negative 50. Whoa. Oh, hey, look, it did simplify a little bit. That's pretty cool. That doesn't always happen. Don't count on it. Sometimes you'll just distribute that guy in and be done. But this becomes, let me see, 5 cancels with that and leaves a 10. So we end up with 2 minus 3 square roots of 6 over a negative 10. Now, some people will bring this minus sign out front, or they'll times top and bottom by negative 1 and end up with negative 2 plus 3 square roots of 6 over 10. These are the same answer, just in a little bit different simplified form. Some people, just like they don't prefer irrationals on the bottom, touchy. They also don't like the negatives to stay on the bottom, and they'd like to keep it all up on the top. All right, now you have a chance to go and look at some by yourself. To the boards! Here are some problems for you to try on your own. Write them down, pause the video, and then press play after you've had a chance to work on them and see how you did. All right, welcome back. Let's do them. Square root of 18 simplifies. This is 9 times 2. So square root of 9 is 3 square roots of 2. And we're going to times that by 3 times square root of 50. Does this have a perfect square in it? It does. 25 times 2. So this is 5 square roots of 2. 3 times 5 is 15. Let's undo that 3 right there. So it's 3 times 25. 3 times square root of 25, so that's 15 square roots of 2. That looks better. And then when we multiply these two together, we get 3 times 15 is 45. Square root of 2 times square root of 2 is 2. This turns out to be a 90. Fascinating. It came completely out of the irrational world. Wow. All right, this one. 3 square roots of 24 plus 5 square roots of 54. These are not like terms and cannot be added until we do this. This is 4 times 6, so that is 3 times 2, 6 square roots of 6, plus 54. Let me see, what does 54 have as a perfect square? Does it have a 4? Nope. Does it have a 9? Yeah, that's 9 times 6. Oh, good. We're going to end up with the same 6 there that we had before. So square root of 9 is 3, so that's 15 square roots of 6. And 6 square roots of 6 plus 15 square roots of 6, that's combining like terms. 21 square roots of 6. Excellent. Number 3, cube root. So we're looking for perfect cubes to come out of here. This one, let me see, perfect cubes are 8, 27, 64, 125. Oh yeah, this is 125 times 2. Good. And this perfect cubes here, they have to have multiples of 3. So we're going to have an x to the 6th and 1x left over. The y to the 9th will 9 divided by 3 will come out just fine. And then z to the 12th is the closest one we get, and then the squared will be left in there. So this guy comes out as a 5. That one comes out as an x squared. That will come out as a y cubed. And this one will come out as a z to the 4th. And what is left in the cube root? The 2, the x, and the z squared. Whew, that looks horrible. Nice job. Okay, the next one, we get multiplication here. So let's multiply these binomials. We get 12 minus 20 square roots of 5. Then move that guy in and we get 6 square roots of 5. Minus 10. Square root of 5 times square root of 5 is 5. Well, it's the square root of 25, which is 5. So we get minus 20 square roots of 5 and plus 6, that's minus 14 square roots of 5. And here we have 12 minus 50. So that's a minus 38. So that is as close as we can get. Excellent. So the next one, 7 over the square root of 11. Here we're going to be dividing, which is rationalizing the denominator. So times by square root of 11, square root of 11, and we get 7 square roots of 11 all over square root of 11 times square root of 11, 11. That's right. Remember, that's the easy one. With a square root, you can just times it by itself on top and bottom. All right, number 6, 3 over the 5th root of x. Now here we're going to times by, we got to take the 5th root of, now we've got to get this up to a 5th power so it can escape the 5th root. So we've got to have an x to the 4th. Yeah, we got to have a 5th root of x to the 4th that we times by on top and bottom. So that equals 3 times the 5th root of x to the 4th is on the top, and on the bottom we now have the 5th root of x to the 5th. Genius. All right, and the last one. We have 2 plus the square root of 3 over 5 minus the square root of 7. We've got to times by something that will clear out the irrational on the bottom, and it will be its conjugate. So we're going to times by 5 plus the square root of 7 on top and bottom. All right. Okay. Yeah, let's put that in parentheses so we can see what happens. So on the top, it's a problem just like what we had in number 4. We get 10 plus 2 square roots of 7 plus 5 square roots of 3 plus the square root of 21. Huh. That didn't simplify or come out at all, but alrighty. So on the bottom, we get 5 times 5 is 25. 5, we get positive 5 square roots of 7 minus 5 square roots of 7. Oh, and look at that. The magic of the conjugate right there. Minus square root of 7 times square root of 7 is rational. It is 7. All right, so let's simplify this down. The top, there are no like terms on the top. So the top has to actually stay as ugly as that. But our goal was to rationalize the denominator, and that's what we have done. So on the bottom, we get 25 minus 7 is 18. And there we have it. Those are the boards. Great. Now you'll be able to go and do your homework.